We were discussing about how to make an amplifier using a PMOSFET, and in the previous class, we went from the small signal equivalent to the full-blown circuit with all the biasing and the incremental sources applied together, right? So this is where we were when we stopped. And we took some values. We can as well take them this time also. So this we assume to be 3 volt threshold voltage. We assume to be 0.5 volt. And then gate voltage obviously had to be less than 2.5 volts. We took 2 volts. And then I further said that the currents that will be decided by mu P C ox W by L VSG minus VTH whole square. I mean, we can do the calculation, but let's assume that for these values of source and gate voltage, the current was like ID sat, which is 1 milliamp. And if we recall, we also started off saying that in order to bias this transistor in saturation region, we had to ensure that the drain voltage was lower than how much? What is the maximum drain voltage? What is the limit of the drain voltage to ensure the transistor is in saturation? It will not be 0.5. I mean, I understand from where the 0.5 is coming. Yeah, 2.5. Yeah, 2.5. So another thing to keep in mind, which is useful, is what is the condition? The condition is VSD should be greater than or equal to VSG minus threshold voltage, right? So you see that source and source are common. VS is common on either sides, right? So this is, I can write VS minus VD is greater than VS minus VG minus threshold voltage. So VS is irrelevant. Essentially, you are looking at the difference between the gate and the drain voltage, or the drain and the gate voltage, right? So what does it mean? Essentially, this, if I flip the signs, this becomes VD is less than VG plus threshold voltage. So you don't have to look into the source voltage at all. The difference between the drain and the gate voltage is what that matters. Okay. So essentially, this also tells you there is a maxima related to the drain voltage in case of a PMOS. Right. So what is the maximum drain voltage to keep the PMOS in saturation? That is 1 threshold voltage above the gate voltage. That's all you need to recall. So we know the gate voltage, that is 2 volts. So 1 threshold voltage above gate voltage is 2.5. So the maximum of drain voltage will be 2.5. So this was all good, and this was biasing the transistor in a proper way. However, this is not sufficient because ultimately we need to ensure that the incremental current flows into a load flows into the load resistor. So we had to put the load resistor. Then we found out few places where we can put and few places where you cannot put based on some practical problems. And then we saw that this is probably the best place to put the load resistor. And let's assume the load resistance value, I think I don't remember how much, but let's assume it's 1 kilo ohm. 2 kilo ohm, let's say. It says 2 kilo ohm. If this is 2 kilo ohm and this voltage was 2.5 volt, what is happening to the drain voltage if the transistor is in saturation? So this voltage is increasing by how much? If the transistor, assuming the transistor is in saturation, then this 1 milliamp will still flow. So that voltage will become 2.5 plus 1 milliamp times RL. So that becomes 4.5. As you see, that's not possible, right? Which means the assumption that the transistor is in saturation itself is not valid. right? So if it's not valid, then no point proceeding. We have to first ensure that the transistor is in saturation. So in order to keep the transistor in saturation, what we need to ensure is that even with the presence of RL, the transistor should be in saturation, right? So which means that in the presence of RL, this voltage has to be less than 2.5 volt. And if I still want 1 milliamp of current, which means the drop across RL will be 2 volt, which means what is the only other thing that I can do? Yeah, this voltage I have to reduce. This voltage cannot be more than 0.5 volt. Right? This has to be less than 0.5 volt, I should say. It should be less than 0.5 volt. So this is all right because this is a designer's choice. I can set the voltages, right? I can set any voltage which is reference to ground easily because it's a battery. Okay, so that is good. Now the question is, if I, let's say, keep the transistor biased in this condition, okay, and let's say I apply a sinusoid of 100 millivolt sine omega naught t, sine omega t. Even before going into the calculations, can you tell me intuitively what can go wrong, or this is okay? Or let's say, I mean, even if I ask what can go wrong, do you think, let's assume that this is not, we didn't apply this, okay? So do you think the transistor is biased at the edge of saturation, or it is somewhere away? At the edge of the saturation. So essentially, if I plot the graph, this is what I am seeing, right? I'm plotting the VSD of the transistor, not this voltage, right? Not the voltage difference between the source and the ground. I'm plotting the voltage difference between the source and the drain, right? So if the VSD of the transistor, the general characteristics of VSD of the transistor is something like this. And the voltage difference of source between source and gate, which is in this case 1 volt, I have selected that 1 volt, assuming that the saturation current is 1 milliamps. So which means that this current is 1 milliamps. And under the condition, under the settings of bias points that I have selected, which means since the transistor is at the edge of saturation, which means I'm probably here, right? So the VSD in this case is how much? 0.5 volt. Because here, if you see, source voltage is 3 volt, drain voltage is 2.5, so VSD is 0.5. And at the edge of the saturation, I have a current of 1 milliamp. Okay. So now whenever you are at the edge of something, you see there is an issue, right? It's slightest amount of variation, which will mean that you are off the cliff, right? When you are, I mean, the example that I give is when you, let's say you have visited a very fancy place at the top of a mountain or top of a hill, and you want to see how far the cliff is. Okay, you can go once in a while and visit the edge, but you don't want to take a walk along the cliff. Slightest amount of breeze here and there, or some push here and there, and you're off. So the same thing goes for any electronic device also. You don't want to bias it at the edge of the saturation. And now let's get into the practical aspects of it. What's going to happen? Let's say if gate voltage from 2.2 volt goes to 1.9 volt. What do you think can go wrong? So let's tackle one by one. Let's assume that transistor is in saturation, right? That's the initial, as always the first assumption, because that is the target. That is our target specification. So we have to start off from the target specification. If I take you back to the first class where I was trying to motivate design-oriented analysis, this is one of the aspects that I meant at that time, that it's not as if 10 different solutions are possible, we start from zero and find out which solution is is the possible solution. We start off with the assumption that the solution is possible. We start off with the answer and then work backwards to see whether the conditions that we have are okay to get me the answer. If it's not, I'll change the condition. I don't need to go and evaluate what the other possible solution can be. Okay, so in this case, we start off with the assumption that the transistor is in saturation and then go ahead and evaluate with the conditions that are given that in fact the transistor is in saturation or not. If it's not, we'll go back and change the condition. I don't need to solve other equations to find out whether if it's not in saturation, what will be the drain voltage, gate voltage, and so on. So that I don't need to do. So under this condition, can you tell me if this goes to 1.9, what is likely to change? Assuming the transistor is in saturation. The current, no, forget about, okay, so will the current reduce or increase? If the transistor is in saturation and gate voltage goes to 1.9 volt, it will increase, right? Because what is the equation? Equation is ISD is half mu P Cox W over L PSG minus threshold volt P whole square. So if I reduce the gate voltage, I'm increasing the VSG. It's equivalent to turning the tap on, right? I'm turning the tap more on, which means that current is supposed to increase. So if the current increases from 1 milliamp to, I don't know, you can calculate how much, but let's say it increases by 20%, it goes to 1.2 milliamps, right? What can you comment on the drain voltage? So it will increase, right? Drain voltage will increase and it will go above 2.5 by another 20% because the current has increased by 20%. If that happens, can you comment on whether the transistor is in saturation anymore? So gate voltage is 1.9 and the current went to 1.2 milliamp. So the drain voltage now goes to 1.2, I mean, those 1.2 times 2 is 2.4, 2.4 plus 0.5 is 2.9, so drain voltage goes to 2.9 volts. So what is the difference between the gate and the source voltage? Gate and the drain, sorry, it's 1 volt. What is the maximum that I can sustain to keep the transistor in saturation? This is the condition. Right? I can go, difference can be as little as 0.5. It cannot be more than that. Okay, so transistor goes out of saturation. The main reason, so I cannot go this side at all. Right? So what is the solution? The solution is to ensure that the transistor is biased away from the saturation somewhere on this side. Okay, so now how much we have to go on the right side depends on how much margin you want to have. Or in other words, how much swing that you are expecting at the output. Right? So in the sense that, okay, let me even take a step back. Why should I bother about swing? So can you now comment on, let's say I bias the transistor at 2 volt and I apply the sinusoidal input here of 0.1 volt sine omega t. What is the minimum gate voltage and what is the maximum gate voltage total under this condition? Pardon? Right. So the gate voltage effectively swings between 2.1 volt to 1.9 volt. So when you go to 1.9, you see that your transistor has gone out of saturation. Okay. So which essentially means that if you know a priori how much your gate is going to swing, then you should bias your transistor in such a way that under the worst case condition also, the transistor is still in saturation. Now, what is worst case condition can differ between circuit to circuit. So that is a designer's job to figure out. But in this case, at least we see that the worst case condition to keep the transistor in saturation is when the gate voltage goes down, because when the gate voltage goes down, you have higher PSG, which means you have higher saturation current. Higher saturation current can lead to increase of drain voltage. The increase of drain voltage essentially is trying to push the transistor out of saturation. Okay. Okay, fine. So that we understand. Now, can you comment on, so let's take some values now, right? So let's assume this half mu p Cox W by L. So this entire thing is 1 milliamp per volt squared. Threshold voltage is 0.5 volt. Okay, so if I have to match the threshold ID set that I had given, I have to change this, right? So we assume VSG to be is equal to how much? 1 volt. So this assumption is not valid. So let's assume this guy is 4 milliamp per volt square. So if I take this set of values, your ISD becomes 1 milliamp, and we don't have to change much in the circuit. So if this is the case, I want to find out what is the incremental equivalent of this network, because ultimately the gain lies in increments, right? Some increment in input is causing some increment in output. If the gain is more than 1, which means the output change should be more than the input change, right? So if you recall again, we arrived at this full transistor-based circuit from the incremental equivalent, right? But now we have to again go back and cross-check if after putting all this, everything into, after putting all the loads and sources and voltage sources together, have I tampered with the incremental equivalent, or that is still valid? So that we have to figure out once again, and then see how much can we get, right? You start from something, you do some change, and you go back and verify whether the original stuff that we started off is still valid or not. So let's say we want to replace this guy with his incremental equivalent. So now help me out. What should I do? So let's start one by one. Let's start from this side. Okay, let's start with the transistor, right? So that is the big elephant in the room. So let's start with the transistor. So we have a nonlinear element. We replace the nonlinear element with this incremental equivalent. So what is the incremental equivalent of our transistor? You can look at your notes and tell me. So transistor has 3 terminals. In the incremental equivalent also, it will have 3 terminals, right? So you have source, you have gate, you have drain, right? So after that, what? Current source between source and drain. Excellent. Value of the current source, or the expression for the current source? Y21 times V source and gate, right? Source and gate, VSG. Direction? Downwards. Okay. Anything else connected between gate and source and gate and drain? Or source and drain? No, in the model of a transistor, do you have anything else connected? Or this is it? This is it, right? We wanted Y11 to be 0, Y12 to be 0, Y22 to be 0. So almost an ideal element that we can get. This is what it is. So this is the transistor. So now you see that we have other stuffs connected. So we have to get the other stuffs also connected to the transistor in the incremental model. So what should I do? Let's start with the source. So what should I connect to the source in the incremental model? In the actual circuit, what is source connected to? A constant voltage source. So what is the incremental equivalent of a constant voltage source? Short circuit. So we short it. Okay. What about gate? So gate has one constant voltage source and one incremental voltage source. So the incremental will remain, the constant goes off. So incremental remains. What about the drain? It's connected to a load resistance RL. I mean, the incremental equivalent of an RL is an RL, right? So that remains, and the incremental equivalent of the other voltage source that is connected is 0. So that shorts off, right? So this goes here. All the shorts are connected together, so I can as well connect it like this. Where am I taking the output from? Across RL, right? So I'm taking the output from across RL, so I can take the output across RL. Okay, fine. So now what is the expression for, if this is VI and this is V naught? Tell me what will be the what will be V naught over VI? Yeah, so right, yeah. So VSG is what? VSG is, in this case, it's minus VI, right? So source is grounded, right? Source is 0, gate is VI. So VSG is minus VI. So Y21 times minus VI is flowing into RL. So V naught is minus Y21 VI times RL. So V naught over VI is minus Y21 times RL. Okay. So what is Y21? You can calculate the value of Y21 and tell me from the values that I have given. You quickly calculate and tell me. So Y21 is CX. So this is 4. No, this is not 4. This is 8, right? This is 8. And the overdrive, that is VSG minus threshold voltage, is 0.5. So this is 4 millisiemens. So Y21 is 4 millisiemens. RL is, how much did we take? 2K times 2K. So this is minus 8. Okay. So you see V naught over VI is minus 8. So what does it mean when I say minus 8? Plus 8, I understand, right? V naught over VI is plus 8. Means it's amplified by a factor of 8. Pretty simple. What is meant by minus 8? What does a minus symbol signify? Right. Yeah. So that's great. So we are essentially, it means that the magnitude wise it's still amplified, but when the input increases, the output decreases. That's all it means, right? It's an inverted sinusoid at the output, right? But does that make sense? Let's say I want to physically understand from the total picture, why does it make sense that when the input increases, the output decreases, and vice versa? So let me draw the circuit again. This is how much? 2 volt. And this is some V battery. By the way, the discussion that we had here was, if this has to be less than 0.5 volt. We didn't say as how less it should be, but how less it should be depends upon how much deviation in drain voltage that you can tolerate. So we'll get to that in a while, but let's assume that this battery is VBAT for the time being. The question that I'm asking right now is, why is it that the negative phase shift makes sense? Exactly, right? So when this guy increases, when the input increases, right? This is sinusoid. So I'm concentrating on the positive half cycle. When the input increases, the gate voltage is increasing. Gate voltage is increasing means PSG is decreasing, right? If PSG decreases, which means the current is decreasing. If the current decreases, what? Okay. Yeah, right. If the current decreases, then this voltage is, the drain voltage is what? Decreasing or increasing? Decreasing, right? So essentially the input increases and the output decreases, right? So another way to look at it is, what is this total current? The total current is whatever ID sat you had, which is 1 milliamps, plus an incremental current, right? So the incremental voltage is VI here. What is the incremental current? So if I look at this picture, the incremental voltage is Y21 minus Y21 times VI times RL. What is the incremental current? Minus Y21 times VI, correct? So in this case, the incremental current will be minus Y21 times VI, right? Why minus? Same logic. When input increases, the total current is decreasing. It's not as if the total, the magnitude of the incremental current has increased, but the total current through the transistor has decreased, right? So which means that if I observe this total voltage, right? If I observe this total voltage, what will I see? Initially, it was probably at, I don't know, maybe 1.9 volt or something. And then when input increased, what's going to happen to the total voltage? It is going to decrease. It is going to decrease. And since it's 180 degree out of phase, this is going to do like this. So the input does like this. And when we say amplification, what we are essentially saying is that this amplitude of the output is higher than the amplitude of the input. We are not talking about DC operating points. DC operating points can be widely different between the input and the output. It's not because just say DC operating point at the output is 2 volt and the input DC operating point is 1 volt. We don't. The amplification factor, if we say is 2, which means if I change the input by 0.1 volt, 0.2. 1 volt, output changes by minus 0.2 volts, right? So it's always the increment, right? So even though it makes sense from the incremental model, but it's still instructive to make the point. Okay, fine. So now let's go back to this guy, and we said that if VI is 100 millivolts sine omega naught t, V naught will be how much? Minus 800 millivolts sine omega naught t, right? Okay, fine. So let's go here. So input is 0.1 volt sine omega naught t. So the output, that is a voltage drop across RL. So this drop will be minus 800 millivolt sine omega naught t. So now can you see the issue? So do you have amount of leverage? Do you have enough margin on the drain voltage so that it swings by 800 millivolts? No, current flow, this current flow is creating the voltage drop. Okay, so the assumption is this, right? If in VI is 100 millivolt sine omega naught t, what is V naught? That is minus 800 millivolt sine omega naught. Okay. So with the way I had biased it here, do you see we clearly see that there is not enough margin, right? Because we saw that the way we had biased, if we bias it at exactly at 2 volt, we don't have any margin at all. Okay. So which means what are the other handles that I can tweak now? Pardon? So let's get to a cleaner picture. So this VBAT was 0.5 volt. This RL is 2K. This voltage is 2. What is 2.5? No, right? 2.5 volt, 3 volt, 1 milliamp quiescent. So now what we are saying is the gate voltage is going from 2.1 volt to 1.9 volt. So if the transistor is in saturation all through the swing of the input, how much will the drain voltage swing by? 800 millivolt up and down from 2.5 volt, right? So this guy will go plus minus 0.8 volt. Okay. So which side is the problematic side? Plus 0.8 is a problematic side, right? So output side going up is a problematic side, input side going down. So in negative from the input perspective. So if this is a problematic scenario, what is the first thing that I should target to make the design slightly better? I could decrease, right? So yes, basically, yeah, I agree. So this voltage is looks like we are working at the edge. So I back off from the edge, right? So I reduce from 2.5. The quiescent need not be 2.5. It can be lower, and it can be as low as, ideally, if I lower it by 800 millivolt, then I'm good, right? But given the circumstances that we have, what is the first thing that you would like to change? Remove this 0.5 volt battery and we make it grounded. So we have somehow gotten 0.5 volt extra, right? So this guy is now at 2 volt, but we still need that additional 0.3. So from where can I get the additional 0.3? Obviously, that is something that I can do. So that essentially, his point is very good, well taken. He's saying that you are having 100 millivolts sine omega naught t. So if nothing can be done, I can simply say that, okay, 100 millivolt was zyada hai. 50 millivolts sine omega naught t, things are fine, right? So we'll settle with 50, right? So that's what negotiations are about, right? So when somebody is telling you that give me an amplifier which can handle an input of 100 millivolt, and you do an analysis and you say that no, cannot be done, you go back and say, can you relax your spec? Right? Cannot be done, can you relax your spec? Then you say, no, cannot be done. So then you have to ask the second question. Okay, if you cannot relax your spec, sometimes they can. Sometimes, but they means maybe your fellow friend who is working on the previous stage, who is giving you this 100 millivolts, I know may not be, right? So if you can convince your friend, fine. If you cannot, then you'll have to go back and see if that cannot be done. What else can we do? Reducing the source voltage means which voltage? You mean this battery? You reduce or increase? Do you want? Okay, so let's reduce that, right? So let's reduce. So if I reduce this source voltage, what is the first thing that's going to happen? Saturation current will decrease. If saturation current decreases, then this 2 volt decreases. All good. So things might be fine. But if I reduce the saturation current, I'm reducing VSG, right? That's how, if I'm reducing VSG, which small signal parameter is getting affected? Y21 is getting affected, your amplification is going up, right? Which means you cannot reduce VSG. Okay. So reducing source voltage, that's why you are essentially saying, never go back again, says, okay, I can give you, but lower gain. Chalega. Right. So you can apply another, you can say that you can apply a minus 0.5 volt battery or minus 0.3 volt in this case. Minus 0.3 volt battery. And you're good. But there's another practical issue. Negative batteries are not very easy to get. Right? You can flip, but you will see later on why I say that. Ultimately, it looks like for one transistor, you have used 3 batteries. And if you have 100 transistors in a network, which means would you use 300 batteries? That's not possible. So the next time you will see that we have to derive all these battery voltages from one source, one battery. We'll do that later, but take that for the time. Yes. So we can step down the voltage. So his point is now I can step down the voltage by using another circuit, right? So how will you step down a voltage? Right. So how do you get a voltage divider? Yes. So if you put a two resistors there, you see you are putting resistances there, right? So you remember the first lecture, second lecture, when we said that we want some output voltage to be constant regardless of load variation and all. And we ended up being, we burned so much current in that load resistance that became the problem. So if you are making a step down thing with a load resistance, with a voltage divider, with a resistance, and that is supposed to take in any current, which means that that resistance should be very low. So basically loading effect, right? So let's not get into that right away. So let's assume that cannot be done. Negative voltage cannot be done. What else? Increase the resistance. Okay, so let's increase the resistance. So if I increase the resistance, can you comment on the drain voltage for the same quiescent current? Same quiescent. Ultimately, I want to keep the same quiescent current because if I change the quiescent current, Y21 is changing. So if I increase the resistance, what's going to happen? It will. So increasing resistance looks like not a good solution because it's decrease it. If I decrease it, what's going to happen to the gain? It's going to decrease. I want the gain also, right? So what else? Okay. So note that, let me give you a hint. So we want to keep the Y21 constant, or rather to keep 1 milliamp current constant, we want VSG to be constant, right? So it's not VS or VS or VG. We want the VSG to be constant. So can you take a hint from there and give me a solution? Change both the source and the gate voltage, right? I can increase both of them. Correct? So I can, let's say I increase from 3 to 3.3 volt. And I increase the gate voltage quiescent to 2.3 volt. So has the current changed? No. So what about the quiescent drain voltage? Has the quiescent drain voltage changed? Current hasn't changed. So has the quiescent drain voltage changed? No. The quiescent drain voltage remains at 2 volts. Right? So how much is the input swinging by? Input is going from 2.2 volt to 2.4 volt, right? So this is the range, 2.4 volt to 2.2 volt. Okay. What is the gain? The gain is still 8, assuming that, or -8, assuming transistor is in saturation. So what is the output voltage swinging by? Plus minus 0.8 still. So which means that it can go to 2.8 or 1.2. Which one is the problematic scenario? 2.8 is a problematic scenario. When does it go to 2.8? What condition of the input? When input goes to 2.2, the output goes to 2.8. Right? So you see that we are better off, but still, I mean, 100 millivolt extra. Right? We want the difference to be less than or more than 0.5 volts. Right? So since the difference between the gate and the drain is now 0.6 under the worst case. So that is still I'm still going into linear region, out of saturation. Okay. So now what is it? What is the next thing? Okay, firstly, let me ask you, do you see it's a problem or still you're okay? So input maximum is 2.2 or minimum input is 2.2 and this voltage is at 2.8. Is the transistor in saturation or not? What is the condition? What is the condition? Where did I write that condition? This is the condition, right? The drain should be one threshold voltage within one threshold voltage of the gate. Threshold voltage is 0.5. How come the difference is 0.6, right? 2.2 volt. There is a maxima condition VD, right? So input is at 2.2. The drain voltage is at 2.8. Okay, let me ask you this way. So let's assume the input is, let's say I take an isolated transistor. Forget about the source. Transistor is open, on, let's assume some voltage which is on. So this is the 2.2 volt. What is the maximum voltage at the drain that you can have so that the transistor is in saturation, assuming threshold voltage is 0.5 volt? 2.7. This is the maximum, right? So which means this VD has to be less than 2.7 if the input is at 2.2 to keep the transistor in saturation. So now basically that transistor is this transistor that is in the network. So do you think it's in saturation? No, right? So by 100 millivolt, we are off. So we can play the same game, right? We basically said that we increased both the gate and the drain voltages by 300 millivolts. I'll increase by 400 millivolts, right? So that's fine. So I increase by 400 millivolts and all specs seem to be satisfied. Okay. But you see, there is an issue. The issue is, this is not an issue in this case. In general, the issue is if you have to gate the gain and if you also have to accommodate for the enough amount of swing, you need a battery voltage which is high enough. Right? If, for example, if suddenly somebody comes and changes the spec and say, I want the same gain. I want the same input swing and the same gain, but RL has to be 4 kilo ohm because RL is a load of some other state. That specification has changed. RL needs to be 4 kilo ohm. So what is the first thing that is getting affected? Your biasing is getting affected, right? If you just take this RL of 2 kilo ohm out and put 4 kilo ohm, you see the transistor is not even in saturation. Because in order to keep it in saturation, to keep the same current, so this voltage has to be then 4 volts. And naturally, nothing is going to work. Right? So if that spec changes, what is it that will go and change? Let's say both the source and the gate voltage I will increase by appropriate amount. Whatever is the appropriate, you calculate and figure out. You analyze and figure out whatever is required to keep the transistor in saturation. But you see that, if you have which essentially means that for a given, if I flip the argument round, I can say that for a given battery voltage, there is probably a maximum amount of gain that you can get. Because if you want to get higher gain, you have to increase the battery voltage. Correct? So what happens in general, current is constant, right? Because we are always taking 1 milliamp current, but I'm increasing the battery voltage. What happens to the power consumption of the circuit? It is increasing, right? So there seems to be a trade-off between having higher gain and burning more power. In this type of configurations, it's not a general trade-off, but in this type of configuration seems to be that we can get enough gain as long as you can give me enough battery of high enough value, and you are okay with burning more power. Okay, so these are some of the trade-offs that circuit designers have to grapple with on a daily basis. Okay. Okay. Any questions so far? Yes.
What was the final conclusion of all this?
The final conclusion of all this is that you don't have a fixed solution. Your solutions is going to change depending on the requirement, right? So if, for example, you want a gain of 8 volt, a gain of 8, and your customer, for example, is telling you that the input swing is 10 millivolt, not 100 millivolt, then you can say that, yes, I can give you that gain of 8 with 100 millivolt with lower power supply also. Right? That is one conclusion. Other conclusion is the one that we discussed. Whenever you are taking up a assignment or a project and say that I want an amplifier of gain of 8, what you have to ask few questions. You cannot simply blindly say that yes, kar denge, right? You have to ask for some other specifications. What are the specifications? What is the battery voltage that you are going to give me? What is the load resistance that I am supposed to drive? How much input swing are you expecting, right? So these are three of the important questions that we see that arises out of this discussion, right? So more or less, if you know the interplay between these aspects, you will be good, right? So more or less, the rest of the course will essentially be looking at the circuits and trying to figure out, if I change one, how does anything else change? Okay. Okay. So before we end, let me delve into the question that was raised a couple of minutes back with regards to, he mentioned something like, why can't we use more batteries, right? As long as it's a grounded battery, it's fine. But there are a couple of issues with that. One is, if you have 10 transistors, which means you need 30 batteries, that's not possible. So we have to derive everything from a single battery. And the other problem is one that I alluded to in the previous class, but didn't give you a solution, is this guy is one source connected in series with the other source, which again is not possible, right? In general, it's a practical problem. You cannot really, I mean, in your ESC 201 labs, you might have seen the sources are this big, right? Big boxes. Then how do you put that in series with some battery? And the other problem is, it need not be an explicit source. So there is some other stage which is driving this stage. For example, your output is this, right? Your output is a voltage across the RL. And let's say there has to be another amplifier which is taking your output and driving it. So for that next stage, this is the source, right? So how do you put this guy in series with another battery when you don't have a floating battery available, right? So which means that you cannot have this configuration. So which means that you have to somehow generate this floating battery. If the floating battery is not available, you have to find out ways of generating that battery voltage. Okay. So again, if I take you back probably to lecture 3 or 4, we discussed something about a capacitor. So if I keep a capacitor and charge it to, let's say, I don't know, 1 volt, or in this case, let's say 2 volt, can this capacitor behave like a battery? Yes, but there is a caveat. Under what condition? It doesn't discharge, essentially, right? I mean, you don't load the capacitor with anything else, right? So if you load it, then it will eventually discharge, and then it's no longer a battery. If you don't load it, then it's a battery. Okay. So now let's say you have a source, and let's say there is no loading. This is what it is. And capacitors, both the terminals are accessible, no issues. So I have the source, I connect in series with the source. So what is going to happen to this voltage? This is 2 volt plus VI then, right? So seems like I can manufacture a floating battery by simply using a capacitor. Okay, but which means that I can, looks like here, this can be a solution, right? So in this part of the circuit, that can be a solution, because I am not drawing any current. Yes?
It will not last for long.
Yeah, so why do you say it will not last for long? Yes, but so what is the discharging path? In this case, at least in the model that we have taken, there is no discharging path, right? So if this model is valid, very important caveat, if this model is valid, then this is going to work, right? But as you must have seen from your experiences, that it's not like you have a leakage zero capacitor or leakage zero circuit. In fact, as it turns out, in modern day MOSFETs also, you have some gate current. So this will not last for long, as you pointed out, which means that we have to do something about it. Okay. So before we break, so can you comment on, now again, this we discussed briefly long time back. Seems like a long time now. So let's say I have a current source, which is sinusoidal. Okay. I have a current source which is sinusoidal. if this capacitor is supposed to act like a battery, in the presence of the sinusoidal current, that is I naught sine omega naught t, what should be the incremental voltage across the capacitor if the capacitor is supposed to behave like a battery? So let's assume that the capacitor acts like a battery, right? So what will be the incremental voltage across the battery? It should be zero. The incremental voltage across the battery should be zero. Battery is holding the voltage, right? It's not allowing to change. Regardless of whatever current you are trying to push in, it will hold the voltage, which means incremental voltage is zero. Now, what we are saying, we don't have a battery, we want to use a capacitor. So if we want a capacitor, what property of the capacitor do you know that can make the capacitor seem like a battery? Large time constant, in this case, there is no time constant associated, but essentially we see that if the capacitance tends to infinity, what is the impedance of a capacitor at a non-zero frequency if capacitance tends to infinity? It's zero, right? 1 by j omega c is the z of the capacitor, right? So if c tends to infinity, then the voltage across the capacitor doesn't change. Incrementally, the voltage is zero, which means it seems like an infinite capacitor can behave like a battery. Okay, again, it goes back to that analogy of, if we assume voltage to be the mechanical analogy, voltage should be a reservoir, right? And you drop some buckets of water inside this reservoir. The height of the reservoir is not going to change if the reservoir is infinitely large, right? On an ocean, if you drop in water, the height doesn't change. So it has to be an infinite reservoir. An infinite capacitor is an infinite reservoir of charges. You push in some charge, it's not going to change. So essentially, it looks like an infinite capacitor can behave like a battery. Okay, so this is where we will stop and we'll start after the midterm. Till today.